Good afternoon, everyone, and welcome here. Thank you so much for your participation.
really the molecules, etc. So we do some approximations, some parametrizations. We put all that on a grid, and in every point of this grid, of this little square, we define the parameters that are interesting, so temperature, humidity, cloud, wind, etc. And then the equations go forward in time until we have the weather for the future, and then we can provide to the Met services, the meteorological services of our member states, who then do the interpretation and provide to the public. So what sort of data are we using? So when we talk about big data, we're already receiving more than 800 million observations per day. So this is really a lot of data to process, and we have to choose which one we put in the model there. When you talk about the weather, of course, you think of the atmosphere, and this is how we started the modeling. The weather comes from, of course, the rain falls from the sky. Now, if you want to go far in the future, you have to take the interactions of the atmosphere with the rest of the world, which is the ocean, the land. So you have evaporations from the ocean. You also have some land effects and some mountains that change the flow, etc. The sea ice as well. So this is what we call the Earth system. This is the same system that are used to model the climate. And if you want to go far enough in the future of weather, that's what you have to take into account. So we have all these data. We have the weather data that people collect in the Met services. So they are balloons, weather balloons. You have synoptic station, what we call synoptics. So they measure at ground level what the weather is. You also have some buoys in the ocean, and you have also, very importantly, some aircraft. So you don't know, but when you're taking big planes, they actually have measurements, and they measure temperature and wind, and they transmit this information. So they are sort of opportunistic observations. So we don't fly planes especially to take measurements, but the planes flying actually take measurements for us, which is very good. And of course, we have satellites. More than 98% of all the data we use are coming from satellites. They are satellites mainly from big organizations like the European Space Agency, for instance, but there are also more and more satellites from the private sector. So the equations used in meteorology, they are not very exotic. They are really all coming from Newtonian physics. So what we call actually our equations is Navier-Stokes equations, and they are nonlinear differential partial equations. And you can solve them numerically, so you don't do a nice analytical solution of these equations. It doesn't exist, but step by step, you go forward in time. So you know what the weather is now, and you integrate the model for an hour. You put the equations there, and you see what it is, and then hour by hour like that, you go for as many days as you want. Because we do that for the weather forecast, which was our main purpose, actually with the same tools, you can also predict flooding. I mean, not exactly the same tools. You have to go to river discharge, etc., but it's the same sort of process. You can predict the occurrence of wildfire. I mean, the probability that there will be wildfire, air quality, CO2 concentrations and monitoring, also climate change. So with the same tools, we go back in time since 1940, and we reprocess, we do a reanalysis, we call it, of the weather. Since 1940 to now, every hour you have an image of what the weather was worldwide. So all this is when I say you have equations and you solve them with numerical predictions. Of course, all that is a big supercomputer, a program to put in a big supercomputer. And this is when we started. So this is a picture of the progress in terms of degrees of freedom no, which one is that? No, I don't know how to press this. It doesn't matter. So you have the number of degrees of freedom as a function of time. So we started to 1 million, and now in 2023 we are 1 to the power 10 or 11. Okay, let's say 1 to the power 10 degree of freedom. So 4 times more degrees of magnitude. So what are the degrees of freedom? They are the number of variables, so I say temperature, humidity, wind, etc., times the number of little grid square on the Earth, times the number of levels. So, you know, the more we refine the grid on which we compute, the more we will have degrees of freedom. What difference does it make? Well, this is what we could simulate in 1985 with one of our first models, and this is what we can simulate now. So these are not satellite pictures, obviously, but this simulates what a satellite would take as a picture. So as you can see much more detail. So this doesn't look anything like weather, but the other one starts looking like clouds over Africa, etc. So it makes a huge difference. So I said we were very deterministic, but we try not to be, because we know that the demon of Laplace doesn't exist. It's an imaginary construction, and we actually have to take into account chaos. And this idea comes in particular from Poincaré, that it can happen sometimes that small differences at initial time can have huge differences in the future. This is all chaotic systems. And it's not just in meteorology, we're talking about finance, and it happens everywhere, not just in physics. But sometimes you have a small difference and it doesn't make much impact, but sometimes these differences can have a big one. And this is what Ed Lawrence, the father of modern chaos, found, that he started his numerical computation by something slightly different, and then he had completely different computations. And so he started developing a theory, and he had this very famous talk: does the flap of a butterfly's wings in Brazil set up a tornado in Texas? So you can imagine a very small change somewhere in a cloud or something, and it can develop a thunderstorm. And we have to take that into account. We can't just be blind and say, yeah, no, we don't care. We think we know what the weather is now, so we know what it is later. We have to take that into account. And this is what we are doing with what we call ensemble prediction. So this is our grid. And instead of just saying we know exactly what it is, we take into account the fact that there are some uncertainties in the observations we have, in the way we compute the image there. So then we say we don't have just one image of the weather, we have 50 of them with very small changes. And from that, then we run the model. So with these different ensemble members, we call them, we run the model. So we ingest that in the computer, and then we have a forecast with probabilities. So we don't say, at least our output is not, it will be 23 degrees in Bologna. It is, the median is 23, but there is a 10% probability that it will be 21, and a 20% probability it will be 25, etc. So this, some people don't like it because nobody likes uncertainty, obviously. But on the other hand, if you're a farmer and you have a crop, and you know that you have to cover your crop if the temperature goes below 0 degrees because it will frost and you will lose everything, you prefer to know how much is the probability that there will be a frost, rather than know on average it will be 5 degrees. 5 degrees doesn't tell you if there is a chance it goes below 0. So that's why we think it's, for people who really want to make informed decision, the only way to do it to have this probability density function of what the weather will be like. So this is a measure of our accuracy and how much we've progressed. So it's a bit complicated, but this is one of our most famous graphs, so I'm afraid I will go through it. So this is the evolution of our forecast accuracy from 1980 to now. And the higher, the better. It's an anomaly correlation between 30 to 100%. 100% would be perfect. We do these curves for different forecast ranges. When we forecast the weather for 3 days ahead, or to 5 days, 7 days, 10 days. The curves for 3 days are higher than for lower range, because the more you go in time, the more you accumulate inaccuracies and the chaos takes place. So we are very good at 3, 5 days, a bit less at 7, and not so good at 10 days forecast. Fair enough. What you see there is the difference between the quality in the northern hemisphere and in the southern hemisphere. That's the difference between the bold and the more fine curves. As you can see, in the 1980s, the quality of the weather in the northern hemisphere of the forecast was much better than in the southern hemisphere. This is because we didn't have all the satellites then. And the southern hemisphere is, of course, covered with ocean. I mean, mainly covered with ocean, very few conventional observations. So we couldn't do a better job than that. But then satellites came along, and we went clever to assimilate, to use the satellite. So at the end of the 1990s, then suddenly you can see that first we improve a lot the quality of the forecast, and also suddenly we do a good job in the southern hemisphere, which is quite good. But what I want to say as well is that what we say in general is that we progress by 1 day per decade. So that's the progress of our numerical weather prediction. What does it mean? It means that the quality of our forecasts for 3 days in 1995 is the same of the quality of the forecast for 5 days in 2025, let's say. So it's low, but it's regular. You know, it's not. It takes a lot of effort to manage to have these 1 day per decade. So this is for the sort of deterministic model. Now we have the same curve for the ensemble, where we have different types of score then. But what you see as well is that you progress, actually for this one, you progress by more than 1 day per decade. And you can see it's not regular. First, in between winter and summer, it's not the same, but also sometimes you have different predictability. So now I'm going to be very proud of my center, because I will say that we are the best model in the world. And it's not me saying that, it's the scores, you know, something. I wouldn't say that if it was not true. And so I have to show it. And because I think this is something Europe should be proud about, you know. In the US, they know our model and they show it on CNN or something like that. They say, this is the American model, this is the European model, because they know that sometimes we predict better than them. And actually, most of the time, we predict better than them. But nobody is perfect all the time. So this is just to show it. It's the same thing. It's the higher, the better. We are the red curve, and the others are below. So you have Japanese, the UK, the British Met Service. You have the German, the Canadian, and the American Met Service. And as you can see, we are quite a lot better than the others. So that's why we are usually quite innovative in our way of doing it. This is because we are not a Met Service per se. We are just concentrating on numerical weather prediction. That's our job. So we'd better do it right, otherwise there would be no point in us existing. Just an example, because we also show some map and we provide to the Met Services. Of course, Emilia-Romagna floods, we investigated it every time there's an extreme event, because I just showed some scores, which is a bit boring, but every day we have some maps, of course, and you can see plenty of maps on our website. They are freely available for everyone. So this is just to say that our forecast did show the red blobs there shows quite a lot of rain for Bologna. It was not, the quantity was not quite as high as what actually happened, but that's because we have a global model, so it's not very fine. But then the Met Service in Italy could refine that with their finer resolution model. But they liked the fact that we could anticipate that a few days in advance. And this is the ensemble model. This is the cumulative distribution function. That is in general, and as the forecast was going, we were really predicting much more rain than average over Bologna. So that's what we're doing. We're doing these forecasts. We send them to the Met Service, and then they use it in their applications. We also go back in time. So as I said, we we go back in time and reanalyze. And even when there were no satellite, by combining model with a few observations, you can predict some of the storms that were there. So this is a very good resource for climate monitoring, and a lot of scientists use it. We also do a European State of the Climate report. So we are not EU organization, but we work a lot with the European Union. And we are what we call entrusted entity by the Union to run 2 Copernicus services. Copernicus is Europe's eyes on Earth, they say. Europe is launching huge number of satellites, and we are running services to use these satellites. So we are doing climate change service and atmosphere monitoring service. Every month we publish a bulletin of what's happening in terms of climate over the world, but also Europe. And every year even more. We also predict the concentration of different particles or ozone, etc., in the atmosphere. And in particular, we can see when there is some dust coming from Sahara then and coming and affecting Europe. So what are the challenges? So that is our gradual, you know, as I said, what we call it the quiet revolution, because nobody knows how much we've progressed, because you're just used to the weather being a bit better. But it's not, there's no step change. It was just very, very gradual, so nobody notices. People expect much more from the weather than they did 40 years ago, but you forget, you just realize when the weather forecast is wrong more than when it's right. So from about 10 years ago, we have a new revolution, which is the digital revolution, which is to try to adapt to new supercomputer and to go to finer and finer scale. This is because when you go to 1 kilometer typically resolution, we are at 9 at the moment, then you can describe much better the deep convection, the big cumulonimbus clouds that you see, that do the big hail, etc. That's where we want to be. In a few years' time, we want to have a global model at 1 kilometer resolution. But this takes a lot of computer power, and we don't have it. And also, even when you have a lot of processor on your computer, you actually don't know how to spread the load, etc. It's complicated. So we have to really work on our software tools to be able to use the new supercomputer, the mega Euro HPC like Leonardo here in Italy, and use the new processors as well. We are using the CPUs, the computing processors. We want to use the GPUs, which are better, use less energy, and the graphical processor units are the ones being developed now. So for this, we have to work a lot on our code, work with software engineers. So for the time being, we were writing our code a bit ourselves. Now we have to be much more professional in what we are doing. But then when we manage to run at 1 kilometer resolution, this is what we can describe, which is really fantastic. You feel that you are there, So this is the wind gusts. This is the ice. You can see the ice almost breathing, cracking there, the little spread in the ice. So this is globally, and this is when you go finer over Europe, when you see the influence of the mountains, etc. You can see the storms coming. So that's what we would like to be. This is a research experiment. That's what we would like to do in operations. So now, where is machine learning coming into it? As I said, we've always used statistics. Okay, machine learning is not just statistics, but we use a lot of physics. I didn't say that when we combine the observations with the model, we use their variance of error. We combine doing optimal control. So there's a lot of stats in what we're doing. And the equations, we don't know them to the highest degree, so sometimes we parameterize, so we use some lookup tables, etc. Artificial intelligence, and in particular, when I talk about artificial intelligence, for us, it's machine learning. It's something that we realized that we needed to use a bit more. So we started using it in little bits. Like, for instance, using data from a satellite from ESA, small satellite, looking at soil moisture and ocean salinity. We didn't have a real physical model to link that to our parameters. So we used machine learning for that. And we realized we have to use it more and more. So our idea in the 2010s was, let's use machine learning in bits of the processing. So a bit in selecting the data, a bit in using the data, and then a bit in the model to accelerate some processes in the model, for instance. Instead of running it physically, you replace it by machine learning. This, we went happily along. We did a whole strategy, a paper in 2021 with this is how we will use machine learning. And then everything accelerated, and we thought, well, no, our plan is not ambitious enough. We really have to put the turbo now and do something else. So this happened in particular because the big tech companies started being interested, and they know much more about machine learning than we used to, and they have a lot of processors and a lot of computing power and a lot of brain power as well. And we had started in 2018 examining what replacing the whole model. So I said, we use the observations, we say what the weather is like now, and then we have this big model, which is very expensive. And we tried in 2018 to replace the full model by machine learning. And we thought, no, it's not giving good results. We let it drop. We shouldn't have. But, we worked at low resolution, and we thought, no, it's giving something, an interesting information, but it's not enough to be really operational. But then, in the meantime, we also defined some data sets, some metrics that people could play with, an open data set. So we do open science, open data. And then people started being interested. Okay, it's not promising, but let's try. And then we had plenty of the big tech coming on to play with it. In particular, NVIDIA. NVIDIA, of course, is selling GPUs, and machine learning is running on GPUs. So they are very interesting to find some use cases where they show, please come and buy our GPUs and do your stuff on our kit. And they started running a machine learning model in research. We had Huawei in China and developed their own machine learning model. We had DeepMind, DeepMind is a branch of Google now, developing their models, and they started being really good. So we thought that's when we had a lightning flash, saying, okay, we can't rest on our laurels now. We have to put, the accelerator and look at it ourselves. So Microsoft, Fengwu, etc., they all got into it, and we got into it as well. And actually, it was very good because I think it's a fine collaboration between private and public, because we are the ones doing the reanalysis of the weather since 1940, thanks to the satellite, etc., from the European Commission, from ESA, etc. Thanks to our model, we are reanalyzing the weather. And this is the resource that all these tech companies are using to train their model. So we are providing the training ground for them to do their modeling. So as I said, this is our typical chain. We have the physics there that links the different observations. We do the initial conditions, the modeling, and then we have predictions. Our idea was, we'll put machine learning in little bits. Let's put it here, and let's put it a bit somewhere, and this way it will accelerate our modeling. But then what we're looking now is really replacing the whole modeling, which is the very heavy lifting part of our processing, by machine learning. And what we do, we are training on these, what we call ERA 5, the reanalysis, the European reanalysis, fifth version that goes back, as I say, 1942 now. And so what we are doing is that training on all these data, and the weather at one time, you also have the analysis of the weather a few days later, so you make the link, and the machine learning makes the link between that. And with that, you learn the equations of motion, actually. So you actually can learn the weather. So that is the training bit. And then, of course, you apply it in prediction. So now, in terms of the costs, in terms of computing power, I'm going to talk about billing units. So it's not money, okay? It's billing units, because that's how we compute the cost of our computer. So ERA 5 is our resource to train the models. It's a huge beast, okay? We put an elephant there. It's 15 billion billing units, because you go back in time, 1940 until now. So it's really a lot of processing. It takes years to produce. So it's a big elephant. Our ECMWF high resolution forecasts, it's 180,000 units per forecast. The machine learning model, 0.3. So, I mean, as you can see, the ratio is really ridiculous in favor of machine learning, that you think you can do so many more modeling with something that costs so little. Of course, it costs a lot when you train it, but you train it once. You don't train it in real time. On the other hand, in real time, it's so much faster, and that's one of the main advantages, of course. But as I said, it relies on the mammoth or the elephant or something, on the training, which still relies on physical basis. So it's a bit of a virtuous circle, maybe. So this is what we are doing then at ECMWF. So we are running a program called Machine Learning with our member states. We are running our own experimental machine learning system, but we are also running the ones from the big tech. So ForecastNet is from NVIDIA, GraphCast is from Google DeepMind, and Pangu Weather is from Huawei, because they give the coefficient and the model in open source. So everybody can run their model if they want to. So what we do, we create the initial conditions. So we analyze with the satellite, we analyze the weather. And from the same initial conditions, we will run our deterministic model, our ensemble model, our machine learning model, and the machine learnings of all the others as well. And we publish that on our web so people can look at them, and in particular the forecasters that use the product every day. And so we have this AIFS, this is our new forecasting system that we run in parallel then. So what, in terms of scores, because I'm going back to the scores because we like them, how do we progress? We always measure the quality and then you have, that's how you progress. So this is a time series of scores, and I will go this one, this is the latest one. So as I said, we are the best compared to the others. This is the red curve, okay? So it's a bit the same as you saw earlier on. Now, what are the machine learning models doing? They are doing this, that, and that. So one is not as good. One is just as good as us. I think this is the Chinese one, Pangu, yeah. And the two best ones are the one from Google DeepMind and ours there. And they are better than our physical model. So that's something we didn't imagine could happen 2 years ago. This is really something that came in 2022 to realize, actually, yes, you can do something very, very useful with machine learning, replacing the whole model. We knew it would do some bits and bobs of good things, but never to replace the good model, because we believe in physics. You know, we've all learned the equation of physics, and that's how we have been trained. And suddenly you realize, well, actually, you don't have to code the physics. Machine learning can learn the physics just by looking at all these previous examples of weather models. This is also an example of the fields coming, and we are working with the Norwegians that also will replace it in a finer grid, because we're working, as I said, on globally. So we are working together to see how you can combine a global model with a limited area model in terms of machine learning. Just to finish, an advertisement of where we are taking it. So I mentioned what we are doing with our member states, but we're also working very much with Europe, not only for Copernicus, but a new program called Destination Earth. And in Destination Earth, we are running these very high resolution models, physical models. We are running them on the Euro HPC machines, in particular Lumi in Finland and Leonardo here. But we are also going to do some machine learning simulations in this program. So the goal is actually to co-design some models together with users. So we call it Destination Earth or Destiny. So we have this Earth system physical, but also machine learning model co-designed with users in different impact sector. So a lot of interactivity. And that's what we are trying to go to, higher resolution and run much more frequently climate models. Because when you know the IPCC is providing their assessment report every few years, they do that every few years, and in between you don't have some climate runs because they take a long time to run. The idea is that there we could almost every year run a climate model and see what the future is going to look like, because we have more computer power and we have adapted our codes. That's the idea of Destiny. So just a summary of where we are then in numerical weather prediction. So I talked about the quiet revolution, where we really made our way, you know, little by little, without any big step change, maybe a bit the satellite in the late 90s. And we progressed 1 day per decade. The digital revolution, we really have to adapt our conventional models to the new supercomputer. And, you know, this will make a difference. But the machine learning revolution is much more recent, 2022, a couple of years ago for us. And now it's fantastic that the PhD student can write a model in a week sometimes. No, maybe not a week, but really very quickly. Before that, to write a numerical weather prediction model, you have teams and teams of scientists working on it and knowing all the equations and all the instabilities, etc. So this is completely different. This is a complete game changer in terms of who can come into the business in a way. For the time being, it was only the big centers like ourselves and the Met services. But now, as I say, the big tech, you know, they just come to us, they say, please explain what the weather is like. We explain what the weather is like, and then they create a model without having learned years and years of PhD in physics. So it's really different. It's a real change, paradigm change. And of course, it also relies on open data and open source. Because how did they make so much progress? Because we provided open data from the 1940s through the EU Copernicus program. Otherwise, they couldn't have trained the model so well. On the other hand, we progressed because they provided their data in open source. So it's just, you know, this is just this openness that make us progress all together. So the next steps, we think the models will continue to have their part to play as a reference, and also really how to go back and analyze the observations. But we really have to improve our tools so that it's better easier to use. And definitely machine learning will play an increasingly large role in our field. And with this, I will stop. Thank you.
So, hello everybody, and Maurizio Monaco here. Before I start, I think that I have to thank Professor Rabier for us, because actually I'm a PhD in physics. So thank you for everything. I mean, I started my university career around 20 years ago, and now I can understand that probably, I mean, there were not, let's say, data science was not existing at that time, so maybe. But at a certain point of my life, I started to be a data scientist. So in a way, maybe I changed my mind. And but you proved with, yeah, exactly. I can combine both. Actually, it's like, let's say, the journey of a person, no, that understands his errors, you know, it makes it, it goes away, no, it goes away from the errors and becomes better. So in a way, but thank you for explaining us this old stuff, and it's really interesting. I have to say, some of the things make us, at least in my opinion, makes us think about very, it's insightful. Thank you, to be honest. So, hello everybody. Sorry for my short discussion about the previous previous intervention. Actually, here I am Maurizio Monaco. I'm co-head of data science in Prometea. I would like to explain you today, actually, after explaining you who is Prometea, what we are doing, especially what we are doing in the field of climate and environmental risk and opportunities, especially giving you an insight on how companies are doing this, especially in the financial services, because Prometea is a company that is mainly active in financial services, and also how we are inserting, in a way, how we are planning our data science and artificial intelligence team to work within the ESG environment, and what we are doing at Prometea in terms of risk, especially in the ESG sector. So, starting from the beginning, actually, Prometea is a company that was established in 1974, so 50 years ago, from a spin-off from Bologna University. And so it has a huge background in terms of research, especially economic research, but then it started to grow up, and actually grew up quite a lot, because nowadays we are 1,100 people with more than 500 customers, more or less all around the world. We are a leading provider of services in Italy, especially in the area that we are showing here. Prometea is mainly active in the wealth and asset management area and the risk management area, especially for financial services, as I was explaining you before. So banks, insurance, asset managers, but also other areas. The interesting fact about Prometea is actually that it also has some research areas, because actually starting from a university, it also has a huge background and footprint in terms of research. And so it has an association that is mainly active also in terms of understanding not only on the financial sector how things are going on, but also in terms of climate, in terms of actually how we are evolving. And so in a nutshell, what is the idea behind Promethea? Because this is very important. The idea behind Promethea is around these three pillars that are the data. Don't know if this works. No? Okay, I'll go this way. So about the data. So data are important and you all know about it. Analytics and software. So we produce softwares that entails the data, and actually they also use the business skills and all the skills, because we are a company of competencies. That's the real point. And actually, so you have to consider these three vertices of this triangle as the business model that is behind Promethea. And so what do we do in terms, for example, of the risk management area? The risk management area is the largest area of Promethea, and actually we are helping the customers, but generally speaking, we are also speaking with regulators and all the let's say the chain of the value chain of the banking and insurance sector about all the different kind of risks that are behind the banks, but also the social and economical substrate of the let's say of the country, and actually we are also active outside of the country. So these are the 9 competence area that we have in terms of risk management, and also we have a competence area that is mainly based in terms of ESG and climate risk, where then this especially competence area supports clients with data, scenario methodologies to assess the change, the impact of climate change, and actually how this let's say has an impact, especially within the financial sector, and also how this impact within the financial sector has to be treated in terms of risk management. So starting from 2020, Promethea has started to design multiple solutions that actually help in a way our financial institutions to fulfill the requirements in terms of what is disclosure and everything, but actually also to make their business more sustainable, and to make their business more sustainable both from a purely let's say economical, both from a way of climate and of social impact and point of view, but also in terms of economical point of view, no? Because there are some risks that consider that you are a bank that provides credit to some industries or some small and medium enterprises, then actually the risks of also the physical risk of the small and medium enterprises are actually your own risk as a bank. Consider, as Professor Rabier was saying before, the flood of Emilia-Romagna. So all the small and medium enterprises were suffering some negative events that actually have put in a strain their business model. No, and so this is something that is especially being more and more important for the business model also of banks. And so what do we do in the end to do this? To do this, we are actually working in the triangle that we have seen before. So business skills, data, and software solutions, so analytics, in a way to construct risk engines that enables us to understand a bit better how the system, all the economical system is working, and integrate all these risks in terms of the climate and evolution within the balance sheet in the end of the bank, because this is what Promethea knows how to do very well, no? And so by means of these risk engines, we are able to, let's say, define which are the risks to which the financial sector in a whole is exposed to. And so, what are these engines looking at? There are two different, let's say, lines in these slides. The first one is about the so-known transition risk. What is transition risk? Transition risk is the risk connected to adequacy to new policies in terms of, let's say, in terms of climate adequacy. Okay, so suppose that, for example, in order to reach your net zero, your net zero, your net zero policy, so that actually all the GHG, so the greenhouse gases you put in the atmosphere, you also subtract enough greenhouse gases from the atmosphere. In a way, you have to invest money. Okay, so by means of investing this money, you risk to be put on strain your business model. No, so this is a transition risk. No, so everything that goes up to adequacy to new policies and everything, or reduce your carbon footprint and everything, include investments. And so actually, the banks, so who want to make credits to you, to provide credit to you, or actually all the sectors might be at a risk, no, in terms if they have to invest a lot in doing things greener in a way with respect to the past, no. And so this is these are the engines that we produce in order to understand by means of at the sector level, so at terms of ATECO, or at level of single small and medium enterprise or enterprise, actually, which is the risk that the people are actually both the enterprises are exposed to, or even the real estate, so the households are exposed to. And so this is the first line. The other instead are connected to the so known as physical risks. Physical risks are actually the risks connected more to climate change and to those that are the physical risk in terms of extreme events that could be like floods, could be like wildfire, could be like all these kind of events. And actually these are connected to especially how the climate is expected to change. We are discussing about a changing climate that has a completely different time window with respect to the one that we were seeing before, because we are looking at climate change that goes to years and years. Okay, so maybe in 10 or 20 years, how the evolution of physical risk is the climate is changing, and also to identify exactly which are the vulnerabilities of your enterprise. Suppose that, for example, your enterprise has different like 4 or 5 plants that are close to rivers, that are close to woods and everything. So it might be exposed to different type of physical risk. And what we do, we actually have models in order to understand how these physical risks put at risk the business of the different enterprises, in order to evaluate this risk and then identify exactly which is the expected loss in case something bad happens. And so these are essentially which are the use and applications that we do of all the activities, the numerical activities that we do with our engines and with our proprietary models. We use these for stress testing, because actually all the it's very important for bank industry to be resilient, to be stress tested in order to be sure that actually even if there are some extreme events, then the banking system stays safe. This usually happens, for example, with let's say interest rates, as we have seen many times, that now regulation is also putting a lot of attention also in terms of all the climate and environmental risks. There are some requirements in terms of ESG disclosures, and there are especially specific requirements for doing this. There are also some strategy in terms of investments that actually banks are doing, and so when they underwrite the credit, so essentially they decide to give a credit to a specific small and medium enterprise or an enterprise, actually they want to understand better the ESG impact that these enterprises are doing. They can also be used in order for an ESG planning and strategy, for example, for decarbonization, or also in terms, for example, of product design. Maybe you don't know, but actually there are some theories about the fact that actually when you invest in some products, financial products, actually there are theories that says that ESG investments are much more resilient with respect to non-ESG ones, and so actually this is very important in terms of design. But then let's go to this is in general what Promethea is doing in terms of climate and environmental risk, but let's go to how data science and AI improve and actually helps in doing this. We have seen how the let's say the risks, how, for example, enterprise risk management in Promethea is doing. You have to consider that data science is providing, as a division, is providing support to all the other 9 areas in terms of evolving these 9 areas with new methodologies, new data, and new activities. Data science division was born in 2017, and actually we are doing both activities towards the outside, so like direct towards customers, but also internal innovation in terms of improving what we are doing within for example, the 9 areas that we have seen in the slide before. A short, let's say, slide about where do we come from as data science division. So we are 65, divided in part in Bologna, in part in Milan, in part in Istanbul, because we have also a large branch in Istanbul. And we are divided between data science, machine learning engineers, and business translators, that are the people that actually understand how to put artificial intelligence within the business processes. And this is essentially which are the activities that we are specialized in. So many activities that are very, let's say, on the edge. We prefer to be, as I said before, for Promethea, we started as let's say, as a spin-off of a university, so research is very important still there. And so we are also trying to keep ourselves on the edge of some specific techniques. Especially we will see how we are dealing, for example, for computer vision, for document processing and text analysis, but we also have we are very active in terms of generative AI, for example, not only for text, ChatGPT and everything, but also to generate data, more specifically, for example, in terms of transactions. No, so which is quite an interesting topic, I would say. But going back to how we can improve the activities, generally speaking, or the risk assessment that we are doing for climate and environmental risk and the ESG competence line, What we are doing, for example, is analyzing satellite data. Satellite data are very important because actually they can provide a lot of new features that are that can be extracted from the images from satellite, and you can segment the image and recognize especially specific areas within the images from the satellite, and also you can identify, for example, evolution in terms of time, looking at satellite data from different time frames, no? And so this can show you how the system Earth, actually, in a way, is evolving. And from one side, and also on the other side, you can detect inside the images specific points that are, for example, terrain elevation or cross-reference with OpenStreetMaps, but also objects, relevant and large enough objects. What do we mean by objects, for example, in this area? For example, you can identify the presence of embankments, or there are specific adaptations from the human in order to reduce the risk of climate, let's say, physical risk, no? So the risk, for example, of a river to flood, no? And this actually is very important in order to understand the physical risk that actually, for a landslide, the physical risk of a specific area, no? And so actually the physical risk of an area where a specific plant is present. Another activity that is more in the area of ESG reporting is actually, for example, connected to the possibility to extract directly information from ESG reports. This is very important because when you want to assess the risk, for example, of a sector, or you want to understand a bit better what's also the ESG risk of a company, it's very important to understand whether there are certifications or specific activities, or, for example, which is the carbon footprint or the let's say whether the energies that is taken by the specific enterprise is taken from renewable energies or non-renewable energies, renewable sources or non-renewable sources, no? So actually this is very important to be done, and this is actually our tools that enables to provide support to analysts to do an easier and faster assessment, that also are a good and important tool in order to improve the products that comes out of the box, let's say off shelf from Prometea. This is actually a live demo of something that we have developed, and is actually important to extract information. No? And this actually comes back to my my final slide, that actually is also a way to launch the challenge that is connected to the next steps. No. Actually, on the 22nd, all the information will be provided to the people joining the group of the Prometea Challenge. But actually, what do we wish to create out of this challenge? Our goal would be to let's say do a design activity in terms of understand how give a step up for small and medium enterprises. At the moment, the preparation of a sustainability report is mandatory only for larger enterprises. No, so what is important could be for small and medium enterprises to understand how they can create an environmental impact score. That can encapsulate whatever type of measure for the ecological footprint, and so actually we will provide to you some information, some data, some examples coming from larger enterprises, and let's say that the mental challenge, not the brain challenge, would be to think and understand how to adapt that ideas to the small and medium enterprises sector, in a way. And so that's it.
Many thanks, Maurizio, and many thanks, Dr. Rabier, for your awesome presentation. So please, Maurizio, don't sit down because I have to call you up on stage because now it's time for the questions, if there are any, but I think there will be some. So if you want to join me, please. Perfect. So, who want to be the first? If you don't ask anything today, it will be very suspicious. And I know you have some strong language skills, so please show it off. Perfect.
For Maurizio, I don't know if I missed it. Most of your data are coming from open sources or from clients. And like the data collection part, how difficult it is.
Oh, you can use the other one. I'll do this for you.
So that's actually a very good question, because for sure we use open data, and some activities you can do already with open data. Other obviously keeping into account all the let's say the legal requirements actually that you have to use, because actually if you use open data you do also have to adhere to all the licenses that are actually needed. No, please be aware of that. Always about reselling or producing, let's say, something that you want to sell out of also open data, which is quite important. But also, yes, they come from customers. Absolutely. So in the sense that some of the data, some of the engines, you know how to use them, but actually when you have to apply the model, no, you have to use obviously customer data that have to be under, let's say, the relevant agreements for treatment of the data. But also we produce internally some specific data out of our research areas. So in terms of, for example, you have seen the climate, let's say the climate model for up to 50 years on. These are coming from data from NASA, but also on top of which there are some Prometheus model that work on that. So yes, generally speaking, we have all the three type of data working together. Again, it really depends then on the specific type of engine, type of area, and everything, which is the most relevant, the most important. But then more or less we have all the three type of data that we need. But then the quest for data is usually always one of the main and most relevant parts of it. You can also buy data if needed. Sometimes this is very important now, because I forgot this part. But actually, yeah, you also buy data, and you can produce data out of data that you bought. But actually, this is also another way. But actually, I think it's also very important to hear your point of view about data and how you collect data and everything.
Sure. So yeah, usually our data is free to use for different met services. As I said, the World Meteorological Organization collects data, redistributes it, and usually a big part of it is available for everyone. Now there also are private companies starting to launch their own satellite and produce their own data, which they sell to different people and that can redistribute it. So we don't have, there are private companies in meteorology that have their own proprietary data, that have finer networks of data that they use to refine the predictions. And we are usually producing a lot of open data, but some of our finer resolution data is actually also to buy. And we have a lot of commercial users actually, including from different sectors and insurance, energy, and plenty of different sectors. So yes, data in is usually open for us, not necessarily for everyone, but all, at least for all the national Met services. And data out is mostly open, especially the ones produced by the European Union. But some of the other very fine and where you provided rapidly weather information is under licenses, and we have a package with a bit of money attached. No.
That's the point.
Yeah.
Any more question?
I want to make a question to Florence, maybe hoping to intrigue a little bit also those of you that are not scientists. I was impressed when you said that the machine learning model is equal or even better than the traditional model. What happens to the people in this moment? Because you really touch with your hand issues like explainability, reliability, and you manage things that cannot be wrong, because if you're wrong, you create a lot of problems. So can you tell me a bit more what happens to the people?
Yeah, there was a lot of skepticism, I think, and saying, well, it will never, because yes, we need to explain as well what it is. But our equations are so complicated in our models that explainability is not, it's an illusion. I mean, you can't, yes, you can say, yes, you can explain because you know the theory. There is this tropical cyclone, it will do extratropical transition, come to Europe, and so it depends on this, etc. But actually, you can't really explain it comes from this or that in the model, in the physical model either, because it's too complicated. It's these 3D, 4D dimensions, you know. So I'm not so fussed about the fact that what they say, it's a black box, you know, the machine learning model is a black box. Well, what we're doing is also so complicated. But yeah, they are especially the people who have been doing physics most of their lives. And in particular, what they look at is the column of air, you know, and so they say, let's change a parameter. Let's say that the surface is not dry, there is a bit of humidity, and so you can see the evaporation. They just look very precisely at all the parameters on one column and when does it create a cloud, etc. And they can play on physical parameter. If I change the distribution of particles in the air, this is what it will do. And this, they can't do it with the machine learning model so well. So these ones are a bit frustrated and say, well, we are going to lose something. But the others, I think we are doing a lot of numerics, a lot of statistics anyway. So I'm more on the part of those who are really excited, actually, because it's, as you saw, the progress is so slow in our field. We had the revolution of the satellites. Now we have the big computers, but this is the first big revolution I see since the satellites, actually. All the rest is a lot of hard work and just improving little by little. And this suddenly, in a couple of years, you have the same quality as what we developed in 50 years. I mean, I think this is absolutely fantastic. But of course, people have to change a bit their point of view. And I still, with some of the method in machine learning, I'm not a specialist, but you can also have some gradient that you find which are the parameters that were the most important. So it's a bit like what we are doing in a way, you know, like what we are doing is, let's say I have a bad forecast. Is it because I had a bad observation to start with? So you remove the observation and you check what the physical model is doing. I think we can do the same in the prediction of machine learning as well. We can find some way to have explainability. So I think people are a bit, they were very skeptical. Now they can't be anymore, but they are a bit scared of losing the control. When you have a physical model, you feel you have control. And this, you have all this training and you feel you have a bit less control. For me, I look at the proof is in the pudding, you know, and is in the eating. So you have all this big pudding. If it's good at the end, for me, I'm a pragmatist probably. But especially when you look at the costs in terms of computer power, and when you look at how much energy you need to spend to run these big models, and we have climate change, and we have to be conscious of using our resources wisely. So if it is a few degrees of order of magnitude cheaper, it would be like even a crime not to use it. I think that's my opinion. But I still believe that we have to keep the physical model as a reference to build some data sets, etc. But so don't abandon it, because it would be stupid to abandon all the knowledge accumulated in so many centuries. But keep it as a reference, but maybe not to do the heavy lifting day after day of the forecasting.
Because that if it works for food, it doesn't.
Sure, that's another specialty. Sorry.
No, if I add something, I really agree with you in the sense that I think that the problem is the fact that physicists tend to rely too much on equations. Now, being a physicist, in a way, I can put that actually physicists tend to rely too much on equations because they have this. I think it's a false sense of control. That's the point, because it's a false sense of control, because actually physics is not why the, let's say, things works in a way, but it's a way to model how things works. No, being a model is actually, you have to understand that from a philosophical point of view, actually it's something that is trying to, let's say, mimic something. Still, there will be at a certain point a new, let's say, a new theory that will be much better than the current one, and actually will be beyond. So that's the point. Probably now with machine learning, we are seeing we can do better predictions, and we don't have already the physics that can be able to do those better predictions. That's the point, because the physics is actually a model of how things from nature works. No, that's the point. We have to. This is my point of view in a way.
I have a question for Professor Rabier about the plot, simply about the plot, the one that showed the predictions, the accuracy of all the models. And I've seen like a sort of seasonality in the predictions, and I want to ask just why that
Yeah,
seasonality.
because in winter in particular, you have these big systems, you have these big storms. Yeah, I think it's this one. So actually what you see, where do you see summer? Summer is here, July, lower predictability. And then January, it's because it's the northern hemisphere, it's not globally. Okay. So in the northern hemisphere, when you have these big systems in winter, so you have these big anticyclone, high pressure, all these big storms coming, they are a bit massive, and they are well represented in model. In summer, you have this convection, the storms at the end of the day that you don't know. There will be storms in the area. You can't really say where it's going to be, and the intensity is more difficult. So the general structures are a bit looser, but on the other hand, you have a lot more instability and variation. So yes, we have this. It's funny because the weather is worse in winter usually, but that's when we can predict it better. So it's a bit paradoxical, but yes, there is this cycle. But this is the northern hemisphere, so of course it would be different in the southern hemisphere.
Thank you.
The difference is amount of correct predictions, right?
Yeah.
So it's between.
Yep. This is at a 5-day range, so it's quite good. But this is the average over a big area. So this is how we measure the quality with WMO. So it's average over 150 kilometers or something, even if the model is finer. It doesn't mean it's not the quality of a very fine prediction. It's of the big features in the atmosphere.
Hi, my name is Chandra, and I have a question about the equation you use in the model. Have you ever think of changing the equation that you use in the model to use a more complicated equation to have more accuracy?
Yes, I think we change the equation all the time, but there are more details in the equation rather than the big fundamental equations are the conservation of mass and energy. So they are the real Newtonian laws. So, I mean, they are the big laws of physics. But when you go finer, you can describe more things. For instance, when we started with the equations in meteorology, we were just predicting wind, humidity, and not precipitation, was just what we call a diagnostic. It was not a prognostic things. We didn't have really clouds. We were saying, okay, if the humidity is 100%, probably there is a cloud. Now we represent the clouds in the model and we make them change with the wind, etc. So we introduce more variables and we introduce more physical processes that we know exist but are maybe expensive. For instance, radiation, so the way the radiation goes in the atmosphere, at the moment it's really more 1D, so the sun is going down, so solar radiation, and then we have thermal radiation going up. We don't take into account the 3D effects as well, like the edge of the cloud or things like that. So these 3D effects, they are very complicated and they are very costly. So at the moment, we don't take them into account, but if we had the computer time, we could. So there are some things that we can improve little by little. And in particular, it was an idea to do the normal sort of radiation in 1D with a physical model, but the 3D effects to parameterize it with a machine learning model, because then it's much faster. So yes, we are always improving. The fundamental equations don't change much, but then we change some aspects and we refine, we go further into details of it.
Okay, thanks.
And I'm Giovanni. I have a question for both. Now there are always more climate disasters. For example, also in Italy, in the 2023, there was the flood here in Emilia-Romagna. And for example, did you expect it? And when do you expect a climate disaster? What's your approach and why people should listen to you? What's the percentual of the disaster that make people go in alert?
Okay, I can start. Yeah, so I didn't say, but we do medium range, but we do also longer range. So every day, 4 times a day, we go to a few days ahead. And then we go to a month, and then we go to the season. And the longer you go in time, the less accurate you are. So for instance, when we predict the forecast on a day-to-day basis, we really say we think it's going to rain and we think it's going to rain a lot, etc. When we go to a month, we just compute more, I mean, some anomalies. So like, is it going to be much more rainy on that week than average? So we can't really say it's going to be really on that day or not. And when we go even to the season, then it's even more difficult to predict. Like we predict the big systems in the atmosphere, like El Nino, you know, this sort of big phenomena in the tropics. But in our latitude, it's so variable that it's a bit difficult to predict. So why should you listen to us? Well, I think sometimes we know we have a good quality forecast. And so we look at the successive forecasts that we start doing 15 days before, 14 days before, 13. And you can see them converging. So you can have a previous warning saying, oh, it's going to be quite, you know, it looks a bit unstable. And then, oh, it looks like there will be a lot of rain in the north of Italy. And the more you go, the more you refine. So sometimes the model changes its mind because we had new data. And what you could see coming, actually, no, it's not going to be there, or it's going to be weaker. But sometimes you can really see it amplifying and amplifying, getting more accurate. So that gives a good indication to the forecaster that it's going to happen. And we don't just provide our model. The forecasters in Italy have access to the model from the American, from others. So they look also, different models have different characteristics. So I think when there is a convergence of the same event is going to happen, then they can be more sure. But for instance, why are we so well known in America is because we could see 7 days in advance the storm Sandy hitting New York. You know, there was in 2011, there was big floods in New York. And this was the first time that a tropical storm was going to hit New York after a while. And the Americans saw it 2 days later. So we were the heroes because we could see it 2 days earlier. But actually all the other models after a while picked up the same solution and also were converging towards there will be this superstorm Sandy over New York. So I think there's a convergence of results that become finer and finer, and that converge between different models as well. But it's difficult for the forecasters because we are just doing the work of producing the forecast. We give it to others to analyze and to interpret and to provide to the public. So it's easier for us to just look at it. And so I know that it's quite difficult because, of course, as soon as you see a possibility of an extreme event, you want to warn the public population. If you do it too often, nobody will be interested in what you have to say. So it's complicated. You have to make it a right judgment of when to start alerting. Yeah.
You had an idea.
Yeah. Yes, absolutely. Yeah, and then the Italian Met Service could run their fine resolution model, which is much finer scale. So then you can see the intensity better. But they were quite happy with the forecasting that we provided.
I say this because a lot of people depend on
Yeah.
save lives.
Absolutely.
People, and this is what happened.
Yeah. And there is this nice initiative from the WMO and the UN Disaster Risk Reduction, which is called Early Warning for All, because we know in our countries how important it is because we are being warned, but not all countries over the world have these sort of warnings because maybe they don't have a Met Service or very few means, and maybe they don't disseminate the information so fast, etc. So the idea of the Secretary General of the UN is that by 2027, there should be these early warning for all countries on the planet because it saves lives.
Yeah, okay. I mean, I think that's really important in terms also to reply to your questions about the difference in timescales. So if you are looking at, let's say, avoiding a natural disaster that is going to happen, okay? So prediction in terms of forecast, you mean that a specific flood will happen in a specific place so you can save population and everything. I think exactly what Professor Rabier said is, I mean, she covered more than I can do. I think that for what concerns instead climate change and actually how forecast, let's say, in terms of more years, no? So let's see how things are going in the next future, but really the next future. There are models that actually, let's say, convey both information about what has happened in the past, but also are exposed to the trends in terms of what is happening and also in terms of specific, let's say, features like increasing in terms of temperature, increasing of or decreasing in terms of water present in the, let's say, in the terrain and everything. And so how things are moving on in order to let's say, do climate forecast that goes up to 20 or 30 years. But then when they discuss about this kind of forecast, it's more like, let's say, a general risk, which cannot obviously, no, it's quite clear, predict specific events, but mostly a general risk of an area in a way. No, that's the point, which doesn't save lives, but can be important for, let's say, for investments, for example, or for other things, no?
Okay, so if there isn't any more question, I'd really like to thank our speaker today for your participation